Now let's look at example 2, and this one states, well, part A, what is the maximum error possible in using the approximation below? And we're given sine of x is approximately equal to x minus x to the x cubed divided by 3 factorial plus x to the 5 divided by 5 factorial when x is between negative 0.3 and 0.3. And we're asked to use this approximation to find sine of 12 degrees, correct to 6 decimal places. And then we're also asked in part B, for what values of x is this approximation accurate to within 0.0005, so 400. So let's look at the solution. So recall the Maclaurin series for sine of x listed in the earlier table. So it's just this one right here, but it keeps going on to infinity. So let's just look at this for completeness and write it out. So this is sine of x equal to summation from n equals 0 to infinity of negative 1 to the power of n. Then you have x to the n plus 1 divided by 2n plus 1 factorial, and then it equals to all of this over there. And yeah, so the next one's going to be minus x to the 7 divided by 7 factorial. The next one's going to be plus, etc. So it's alternating, and the radius of convergence is infinity. So I'm just going to write this out like this. So this equals to sine of x, is equal to, when you go to infinity, so it's going to equal to, it's going to be x minus x to the 3, then 3 factorial plus x to the 7 over 7 factorial, and yeah, it keeps going. This is plus 5, the next one's 7. This is 5, and then the next one's going to keep going on and on. Next one's going to be x to the 7 over 7 factorial plus dot dot dot. Goes all the way to infinity, and again the radius of convergence is infinity, so for all values of x. Yeah, so note that this series is alternating for all non-zero values of x. So when you plug in 0 here, it just goes to the trivial equals to 0. When you plug in anything else, it's going to be alternating, and I'll show you, make a table like this, just show you. In my calculus book, it doesn't actually do this. They just say it, and that's pretty much what they say, but let's just go for a completeness. So if we have n like that, I'm going to start off as this is n equals 0, n equals 1, 2, 3, etc. Just the usual count from 0. So I'm going to do this, and I'm going to write this as just the ones that affect the, I'm going to call this plus or minus. Or actually, we don't need to write plus or minus. We just write, because it's alternating, we're going to put negative 1 to the power of n, like that. And the next one's going to be x to the power of 2n plus 1, because it's going to be going in odd power. So when you have n is 0, for example, let's put it like this. So when n is 0, you're going to have a negative 1 to the power of 0. It's going to be 1. And then next one's going to be x to the 1. So that's just the first term. So we could just ignore this. Is just equals to 1. So we get x to the 1. That's just equals to 1, like that. And the next one right here is going to be, now if we look at when x is less than 0, so what ends up happening here is the sign is going to be, well, negative. It's going to be negative like that when it's less than 0. And the next one's going to be when n is 1, we're going to have a negative 1 to the power of 1 is going to be negative. Then x to the power of 2 times 1 plus 1 is 3. And then when x is less than 0, we're going to have negative times by negative equals to positive. So notice the alternating there. It's going to be positive, like that. And the next one's going to be n is 2. So the second one right here, n is 2. We get negative. This is going to be just positive. So it's going to be positive, and then x to the 2 times 2 is 4 plus 1 is 5. So you can see that it's adding up every odd power, like that. And then when you plug in negative, it's going to be negative, like that. So notice this negative plus negative, the next one's going to be, well, the same thing. This is going to be negative x to the 7. You can see the pattern. The next one's going to be, well, plus. It's going to be negative times a negative. It's going to be plus, etc. So you're going to go negative plus, negative plus. And then when x is greater than 0, just the other case, what we're going to have is the first one's going to be positive. The next one's going to be, well, negative times a positive. So we're going to have a negative times a positive, which equals to negative. So we have plus, negative. Next one's going to be x to 5. This is going to be just positive. Next one's going to be negative times a positive. That's going to be negative. So notice that this is alternating. So these are both are alternating for all values of x when x is not equal to 0. So this is alternating. Alright, so now going further, so the successive terms decrease in size because the absolute value of x is less than 1, because these terms, so x, then we have x to the cubed, x to the 5, because x is less than, the absolute value of x is less than 1, so it's 0.3, yeah, because it's between negative 0.3 and 0.3, that means you're also going to be multiplying by fractions. For example, this is 0.3, 0.3 times it by 0.3 is going to be smaller than 0.3. Also going to get smaller, 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 and this is approaching zero as this power goes to infinity. So you're just going to be multiplying more and more of a fraction. So and their limit approaches 0. So we could use the alternating series estimation theorem, and again, just recall again from it. Basically, so the terms of bn plus 1 is going to be less than or equal to bn, so it's getting smaller. This is the alternating series test, so each one of these terms is getting smaller and smaller. The next one is going to be less than the previous one, and the limit is approaching 0 of the bn, so these terms are getting smaller and smaller. Thus, the remainder is going to be at most the next term. So if you're going to be looking at the partial sum of this up to the this is up to the fourth one right here, so the fourth partial sum, it's going to be at most the error is going to be the next term, so b5. So in our case, yeah, so what we'll have is, let's scroll down. So, yeah, so thus the error in approximating sine of x by the first three terms of its Maclaurin series is at most, and it's going to be, well, yeah, it's going to be at most. I'll just put this like this. This is, so if we have the remainder Rn like that, it's going to be at most Bn plus 1, so the next one. So in our case, because we're starting off at, so n is 0 there, so that's the first one. So this is going to be, for approximating with from up to the power of 5, that's going to be R2, R sub 2. Yeah, and then we're going to be using the next term, which is going to be x7 divided by 7 factorial as the maximum error. So in our case, we're going to have R2, absolute value, the absolute value of the remainder of the second, or of the n equals to 2, or for 3 terms. Yeah, starting at n equals 0, yeah, using the Taylor series is going to be at most. Now it's going to write this as, yeah, as the next term b3, which in our case is going to be absolute value, because we're taking the absolute values of it, 7 over 7 factorial. So that's the next term over here, the absolute value of that. And now that equals to, well, this is going to be equal to absolute value of 7. Divided by, and then 7 factorial is going to be 5040, and I'll do a calculation check. And yeah, here's a quick calculation check, so just press space like that, so 7 factorial using the one-note calculator, so 5040, like that. And now if x is between negative 0.3 and positive 0.3, then the absolute value of x is going to be 0.3. So the error that this value can be is going to be smaller than, it's going to be basically this right here. I'm just going to write this fully R2. It's going to be less than or equal to, it's going to be less than or equal to, and we're going to write this as 0.3, the absolute value. It's going to be 0.3, actually that is the absolute value, 0.3 is positive. So 0.3, and now we're going to go to the power of 7 divided by 40, and now this is approximately equal to, and it's going to be 4.3 times 10 to the power of 8. It's approximately equal to that, or you could just write it as less than, because it's actually a tiny bit more. Yeah, so you just put less than that over there. And let's just circle this out right there, and we're going to do a calculation check as per usual. And yeah, here's a calculation check to show this error. So we have over here calculation check. Just use DuckDuckGo search calculator. So you just search it up, and it gives you this answer. Because my OneNote doesn't get this fine. It will just give a 0 answer because it's the power of negative 8. So this is going to be, if you type it in, 0.3 to the power of 7 divided by 5040. This is going to be 4.339 e negative 8. This is just, yeah, I mean, note most calculators use the notation. Yeah, use the notation, for example, e to the 8 as being 10 to the negative 8. So this just means 4.339 times 10 to the 8. And yeah, so that is correct there. So to find sine 12 degrees, we first convert to radians because it's in degrees. So scroll up to what we're asked. So we're asked right here. Let's go over to part B. Yeah, there it is. I just teleported over here. So part B, for what values of x is this approximation accurate to within? Actually, no, that's not part B yet. This is the that's part B after. Uses approximation to find sine of 12 correct to 6 decimal places. So let's start solving this one. So to find sine of 12 degrees, we first convert it to radians. And the reason for that is this function is derived in radians. So this is in radians. It's usually by default unless otherwise stated. So this is in radians right there. So let's just solve it. Yeah, so sine of 12 degrees. So sine 12 degrees. This equals to sine of 12. And I'll put a degree sign like that, times it by pi radians. Remember, pi radians is 180 degrees. That's just a half circle, so a full circle is 2 pi. So this is going to be pi radians, like that. And this is going to be 180 degrees. So then this would cancel with this. And also this one right here would cancel. Divided by 2 is going to be 6. Divided by 2 here is going to be 90. This is going to be divided by 2 is 6. Like that, and then divide this by 3. You get divided by 3, you get a 2, and divide this by 3, you get a 30. So you get 2 over 3. But then you also keep going. So you can divide this out by 1. This one then divided by 2. You divide 2 by 2 equals 1. Divide 30 by 2 is equal to 15. So just speed up the algebra there. So sine, this is going to equal to sine of pi 15 in radians over 15. And usually, yeah, just written like that. And then we could just ignore the radians. Yeah, because that's ignored. Yes, yeah, so just assumed over there. So thus, now we could plug that in. That's our x value. So this is going to be our x. So we're going to have sine of 12 degrees is equal to sine of pi over 15 radians. And this is approximately equal to, or approximation of pi over 15 minus pi over 15 cubed. Yeah, this is our approximation. So we're going to go this one right here, cubed divided by 3 factorial, then the next one's plus x to the power 5. So let's just approximate it. This is going to be times it by 1 over 3 factorial, like that. And then the next one's going to be plus, now we're going to have pi over 15, power of 5, times it by 1 over 5 factorial. Like that. So yes, epic stuff indeed. Now if you calculate this out, this is going to be approximately equal to 0.2079169. And we're only asked the 6 decimal places, and that's going to be, so it's going to be 1, 2, 3, 1, 2. So we could just round this up to 912. And again, it's going to be accurate within over here. So 4.3 times 10 power of negative 8. So it's going to be accurate within that. But we're only asked to correct to 6 decimal places like that. So let's just do a calculation check on this. Yeah, so here is the calculation check right here. So pi over 15, again using my OneNote calculator, minus pi over 15 cubed times 1 over 3 factorial plus pi over 15 to the power 5 times 1 over 5 factorial. And that's our answer. Let's press delete, press space. Yeah, so it gives a big giant one over here, 7169. So there it is over there. And then we'll just delete this to match up with what my calculus book has, which is this part. And then also, if you put sine of 12, this is in my sine function uses degrees in the OneNote. So this is going to be sine 12 equals to 0.20791169. So it's very, very accurate there. Let's just see. I'm just going to put space equals space. So that's how accurate it is up to there. Let's just compare it exactly. So delete and press space. And what do we get? We get 69. Then there it is. All the way to the 4 is different than this one. And let's see how many points. Yeah, and as expected, this is literally 4. Yeah, this is 8. This is 10 to the power of 8 and negative 8, like that. So in other words, 8 decimal places, and then there's a 4.3. So it's exactly accurate. 4.3 10 to the negative 8, which is quite fascinating stuff, guys. Yeah, so, but we were only asked 6 decimal places, so thus correct as 6 decimal places since our estimated error is within 8 decimal places. We have sine of 12 degrees is approximately equal to 0.20791 and rounded up to 2. Yeah, so fascinating stuff. And now let's look at part B. And part B says, for what values of x is this approximation accurate to within 0.0005? To see yes. So now instead of using this, we're gonna have to find this range right there, or this domain, for a given accuracy. So let's see what we can find. Alright, so let's look at part B. So the error will be smaller than 0.0005. This is going to be, yeah, it's only, I think there's another 0. Let's just double check that. There's another 0. Yeah, so 4 zeros. So it's only going to be within it when, yeah, it's going to be, the error will be smaller than it if, and we just look at our typical, the remainder using the estimation theorem, which was the absolute value of r sub 2 of x is less than or equal to absolute value of x power 7 over 5040. So now this would be less than 0.0005 when this error, yeah, is just going to be less than 0.005. So we just make it given that it's less than 0.005, and now we can just solve for the x values. And I can move this over to there, and then what we'll get is thus what we get is absolute value of x to the power of 7 is going to be less than 0.00005 times it by 5040. And now this is going to be, well, let's just calculate this by manually. Let's see what we get. Let's just put a bubble like that. This is going to be 5040. Instead of just using a calculator, let's just do some algebra for fun. So 5040 times 5, then 5 times 0 is 0, 5 times 4 is 20, so it's 0, 2, 5 times 0 is 0, add 2. So then now 5 times 5 is 25. So we get 2520, and that's how many zeros? This is the 6 decimal places right there. I mean, that's 5 decimal places. So this is going to be, 25200. So in other words, this is going to be less than, and now we have to move it 4 decimal places. Oh, this is 1, 2, 3, 4, 5. And this is 5, like that. So it's going to be exactly matches. Yeah, or you could just divide this by 5 decimal places. So in other words, we're going to have to move this 5. So if this says 5 like that, then this calculation would also need to go 5. It's going to go 1, 2, 3, 4, 5. So let's do that again. So it's going to be 1 decimal place, 2, 3, 4, and then 5. So it's going to go all the way to the 0.2. Yeah, so the decimal place is going to be over here. So it's going to be right over here. Decimal place 0.252. And yeah, let's erase this, and you could try it yourself. It's going to be exactly that. So, in other words, now to solve for x, we have to do take the 7th root of it. So, absolute value of x is going to be less than, and now we just do 0.252 power of 1 over 7. Like that. And let's just move this over. Let's move it down a bit, and let's rewrite this 1 over 7. Put this a bit better. 1 over 7. 7 is not good enough. Okay, that's good enough. This is approximately equal to, when you plug in the calculator, 0.821. And I'm just going to circle this part right here in my light circle. And yeah, here's a quick calculation check, and might as well calculate both of the other ones too. So this is going to be, I'm going to circle this 0.821, and this is going to be 0.252 power 1 over 7 is equal to 0.8213. Just put this equals 2, like that, so you can see the calculation. And also you could see if you go 0.00, let's do this better. 1, 2, 3, and then 4, 5 times 5040 equals, and then it is 0.252. So yes, that is correct. So the given approximation is accurate to within 0.00005 when the absolute value of x is less than 0.8. So remember, this is the absolute value of x there. So we found this is beyond our 0.3 values. Yeah, so basically this one right here is for when the x is between negative 0.3 and 0.3, but if you want to get past that, the error is going to be 0.0005 when it's x is when x is at most 0.82, like that. And here they just rounded up, yes, 0.81, and it's rounded down actually at 0.82. So anyways, let's keep going further. And now this is a part of the example 2 where we're going to solve the approximation instead of using estimation theorem, the alternating series estimation theorem, we could use Taylor's inequality. So what if we use Taylor's inequality to solve example 2? So yes, so solving for the derivatives of sine of x we get, and the reason is because, just scroll up over here. So this is our approximation. Where's the approximation? So this is our approximation up to the x to the 5, and then the next term is the x to the 7. And recall that the Taylor's approximation, let's just scroll all the way to it, just for completeness, just to refresh. So this is the Taylor's approximation. Remember, this is for the fn+1 derivative, and it's less than equal to 1, and then the remainder, absolute value of the remainder is going to be less than or equal to m divided by n+1, and is x to the x minus a to the power of n+1. So in our case, the highest derivative is x to the 5, and the one right after is x to the 7. So we're going to have to find the derivative. Let's just scroll down. Yeah, let's just scroll down here. So this is to x to the 5. Remember, there's a bunch of zeros in there where there was x to the 4, x to the 2, etc. And also the next term is going to be x to the 6 will have a 0. So so this is going to be our largest derivatives. It's going to be x to the 5, or the n equals 5 derivative. And then the error is going to be, we're going to use this as the value for m. So the 7th derivative, like that. So if we use if we use Taylor's inequality, what we get is we have to solve for derivatives of sine of x. We get, let's just go for a fun adventure right here. So f of x equals sine of x, like that. Write this better. The derivative f prime of x, recall, is just going to equal to, this is going to be negative. Actually, no, it's not negative, it's just cos. So the derivative of sine is cosine of x, and then the second derivative, f double prime of x, is equal to, the derivative of cosine of x is equal to negative sine of x, like that. And then the next one is going to be equal to, this is going to be negative cosine of x. And then the fourth one, like that, is equal to negative cosine of x is going to be negative times a negative. Yes, yeah, cosine of x is negative sine of x, but there's already negative, so it becomes positive sine of x. And the pattern repeats. So f to the 5, the fifth derivative. Fifth derivative is going to be of x would equal to cosine of x. F to the 6 of x. Yeah, f to the 6, this equals to negative sine of x. So then what we get is the 7th derivative, where we're going to use for our m value, like that. Let me just do this a bit better. The 7th derivative of f7th derivative f to the 7 of x is going to be negative cosine of x, like that. So this is what we will use. Alright, so now since cosine and sine functions oscillate between -1 and 1, we can apply Taylor's inequality accordingly. So just recall, and we don't need to worry about cosine the graph, because that is the 7th derivative over there. So recall, if you just have a cosine like this, if this is x, this is cos of x, and if we have a line like this, dash 1, this is equal to 1, and at the bottom is going to be, this bottom is going to be -1, like that. This is -1, and what we have is, remember, just recall, cosine just looks something like this. Yeah, so it just goes like that. So it's always going to be within 1. So in other words, we have, in other words, we have cosine, the absolute value of cosine of x. Let's put this like this, absolute value of cosine of x is less than 1, or less than or equal to 1. Yeah, so thus in our case, we have the 7th derivative like that is equal to negative cosine of x. So thus, the absolute value of the 7th derivative, this absolute value of x, this is going to equal to the absolute value of negative cosine of x, which is the 7th derivative, cosine of x. And now this right here is going to be less than or equal to, well, 1. And this is going to be our m value. So we'll just choose m is equal to 1. Yeah, so thus what we have is the right here, the remainder, the r6. Actually, that's a derivative. So put this r, this r right here, r6 of x. And again, remember we're doing r6 like that because even though this one is the 5, so let's go back. This goes to the 5 right here. The next one's going to be a 0. So it's in other words, the 6th part is going to be a 0. The x to the 6 will have a 0 derivative when you plug in a equals to 0. So in other words, so that's why the next one, notice here, in between is a 0. So that's why even though this is the 5th part here, where the estimation is the same as the 6th. So it's actually the 6th. And then the next one after that is 7, because the 6th term is 0. So let's keep going further. So this is going to be less than or equal to m, then n plus 1, like that. And this is going to be absolute value of x minus a. Just for completeness, it's going to be x minus a, n plus 1. And in our case, it's going to be less than or equal to, well, 1 over 7 factorial. Now x minus a, the a is 0. This is just a Maclaurin series. It's going to be absolute value of x to the power of 7. And notice this becomes x to the 7. Remember, 7 factorial is 50, 40. This is exactly as our estimation, as our alternating series estimation theorem. This is exactly the same thing, which is fascinating stuff. So fascinating. So this is the same as before. Thus we get the same estimates as with the alternating series estimation theorem. Yeah, that's exactly the same thing we just had for the whole time. So there's our x power of 7 divided by 50, 40 in our estimation theorem. Anyways, just keep going further. Yeah, so now continuing on to this example 2, what about graphical method? So we can graph the following remainder function, and in our case, we're going to write this as r. So the remainder, remember, this general formula for remainder is r sub n of x, absolute value, is equal to the difference between f of x and our approximation t n of x, the Taylor Polynomial. So in our case, using the same methods as the Taylor's inequality, they're the same notation, so r6 of x like that. And now in the estimation one, we just use r2, but again, that just depends on how you're counting. So this one's r6 like that. This is going to equal to, well, f of x is going to be sine of x. And then we're going to minus now, this is going to be minus x minus x to the 3. 3 factorial is going to be 6. This is just 3 factorial, 3 times 2. Equals 3 times 2 times 1. And the next one's going to be plus x to the 5 over, well, 120. Absolute value. And this is, again, this is going to be 5 factorial, which equals to 5 times 4 times 3 times 2. Yeah, times 3 factorial. So that's a 6. Yeah, so that's going to be a 6. So we're going to have a 6 times 4 times 4 times 4 is a 20. And 20 times 6 is 120. Yeah, so that's 120. So that is our graph. So we're going to graph this remainder function. Alright, so now let's just graph this out. So we can graph the remainder and compare it to the maximum error determined in example 2a, which was that 4.3 times 10 to the power of negative 8. So this was the maximum error there in in example 2a. So here's the Desmos calculator here. So what I've done here is, let's just see what I've done. Yeah, so we have sine f of x equals to sine of x is the, actually that's afterwards. Yeah, that's the function. So here's the one in black is the r6 of x equals to f of x minus t of 6, like that. Which is just this part right here, x minus x cubed over 6 plus 5 x to the 5 over 120. And notice what we have here, and I also have graphed y equals to the maximum error 4.3 times 10 to the power of negative 8. and so that's this part right here. So that this one is y equals to 4.3, the highest error. In example, this is going to be, let's put this better. Y equals to 4.3 times 10 to the negative 8. That's this line like that. We'll put this like that. So that's that line. And also graphed x equals to negative 0.3 and x equals plus 0.3. And notice it's exactly at this point right there. These are almost exactly at there. So you can see graphically that it's within this error. So this function right here, though, or this remainder, is within these two error bounds like that. So it is within this whole thing, which is quite fascinating. So we see from it that, or from this graph, that the remainder R6 of x is less than 4.3 times 10 power of negative 8 when x is between is less than or equal to 0.3. So it's between it, it's going to be less than. This is the same estimate that we obtained in example 2a. And now for part B, we want R6 of x is less than 0.0005. So we graph both y equals R6 of x and y equals to 0.0005. Again, note that the notation, this is 6, the other one we called it remainder R2. But again, it depends on how you're counting. It's one of those counting a bunch of the zeros that are not shown anymore. And again, that's because we were looking at the 7th derivative for the Taylor's inequality, and might as well just keep it. So anyways, so now what we have here is, so we're going to graph, now we're going to graph y equals to 0.0005, so that's this part right here. Y equals to 0.00005. Let's move it somewhere a bit better. Yeah, y equals to 0.00005, like that. And here I've graphed negative 0.82 and also 0.82. This is our x equals to negative 0.82, and this is our x equals to plus 0.82, like that. And you can see that those are the vertical lines, the other one's horizontal is the error. That's the approximation, or the error. Now you can see it's within the negative 0.82, and you can see this is the error R6 of x, and it's exactly within that. So those are the graphs there, and it was just quite fascinating stuff. So it's still, again, within this error bound between those two values for x. So plotting x equals to plus or minus 0.82, we find that the inequality is satisfied when absolute value of x is less than 0.82. Again, this is the same estimate that we obtained in the solution in example 2b. Yeah, 2b, and that's, let's just see that one again. Yeah, there's our earlier one, 0.821, or just 0.82, like that, rounded down. It's just fascinating stuff. Yeah, so now going further, so if we had been asked to approximate sine of 72 degrees instead of sine 12 degrees in example 2, it would have been wise to use a Taylor inequality, or use the Taylor polynomials at a equals to pi over 3 instead of a equals 0, because they are better approximations to sine of x for values of x close to pi over 3. Notice that notice that 72 degrees is close to 60 degrees, or pi over 3 radians. And the derivatives of sine of x are easy to compute at pi over 3. So that's yeah, you could use our exact trig ratios. And we can graph the following Maclaurin polynomial approximations for sine of x to show how they get further apart as you move away from your starting a value. Yeah, as your starting a value governs the start of the approximation. So yeah, let's graph the following Maclaurin polynomial approximation. So for sine of x, let's say t1 of x. This equals to x like that. And then let's go with t3 of x equals to x minus x3 over 3 factorial. And if you count the zeros, it's the same thing as writing to the 4. You can also, this is the same thing as writing to t to the 4, and this one would be t to the 2 because the next one would be 0. But anyways, we'll just ignore that. Just put it as my calculus book has written. Now the next one's going to be t to the 5 equals to x minus x to the 3 over 3 factorial plus x to the 5 over 5 factorial. And then the next one's going to be t to the 6 x, t to the 6x like that. And this is going to be x minus x to 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial. So let's graph all of these out. And this is a 7, not a 6. Yeah, it's a 7 or an 8. This is a T5 or a T6 because the next one's a 0. So let's graph this out. And here if we graph with the Desmos graphing calculator, so we have fx equals the sine of x and dashed line like that. It's dashed line across there. So now the first one, t1 of x is in red, and that is just a linear function. Notice that it's approximately sine of x near 0. The next one, t2 of x is equal to, yes, it should be, yeah, here I quickly just pause the video and, yeah, quickly pause it and just fix up these notations here. So T1, T3, T5, T7. Yeah, so just fix those subscripts up. So yeah, we can see that fx is the dashed line, a sine function, sine wave. And then we have T1 of x is the red linear line. Then we have T3 of x is the blue one. And notice it's better approximation than linear. Then T5 of x is going to be in the green. Notice it's approximately over here, so it's better approximation. And then T7, notice T7 is very close all the way past the x equals to 2 there on this right side. Then also, yeah, it gets to over this part here, which is, yeah, past the x equals 3 part. So, x is less than -3. Yes, fascinating stuff. So you can see that as n increases, Tn of x is a good approximation to sine x on a larger and larger interval. So again, if you this is starting at a equals to 0. So that's at a equals to 0. So if you want to start off, if you want to be a better approximation elsewhere, so instead of going to t like t100, you can just go to start at a equals to 4, for example, and then you can have a better approximation here, and it goes outwards, and so on. So you could change up where you start off from. Yeah, so Tn of x is a good approximation to sine of x on a larger and larger interval. One use of the type of calculation done in examples 1 and 2 occurs in calculators and computers. For instance, when you press the sine or e to the x key on your calculator, or when a computer programmer uses a subroutine for a trigonometric or exponential or Bessel function or other complex functions. In many machines, a polynomial approximation is calculated. Yes, fix up the typo. So yeah, it's going to be just using this same exact method. So instead of going sine x, we'll just convert it all into polynomials, which is easy to calculate. X, for computers, x to the x minus x cubed divided by 3 factorial. These are all just simple calculations that, yeah, as opposed to sine of x or any other complicated function. Yeah, so that's what it's used. So the polynomial is often a Taylor polynomial that has been modified so the error is spread more evenly throughout an interval. So yes, so it's going to be just Taylor polynomial, and then also make some other methods to split this up so that it's not just at this point. You can get an a or a mix of a starting at 0. Then once it gets past a certain point, you can change up that a value. So you can go a4, a6, etc. It's just fascinating stuff.